SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome back to the aerospace structural analysis. Today we will be going to lecture 6, the second week, first lecture, which is lecture 6. It will be the torsion of non-circular shaft, which we started in the last lecture and will be continued in this lecture. So, let us assume a shaft which is shown here, which has a non-circular cross section. So, this is the cross section, this is any arbitrary cross section XX of the shaft, which is non-circular in shape and can be any arbitrary shape, as I mentioned in the last class. So, similar to circular cross section shaft, this will also be in pure shear, where the shear stress tau is acting at any point P, and the shear stress can be resolved into two components in the Cartesian coordinate, that is tau xz and tau yz. And according to Sand-Venant's theory, the displacement fields for a non-circular cross-section shaft is given as u, v and w, where u and v are exactly similar to that of a circular cross-section shaft, except that w, which is the displacement in the lengthwise direction, is non-zero here, and it is given as theta into psi x comma y, where psi is the warping function which governs the out of plane deformation of the shaft in the lengthwise direction or in the w direction. So, we have seen that in order to for this displacement fields to satisfy the governing equilibrium equation and the boundary condition, they need to satisfy certain constraint, which we have derived in the last class. So, I will just rewrite it to summarize what we did in the last class. So, in the last class we have seen that the warping function psi needs to follow these two criteria. So, in summary, we can say that we, in order to implement Sand-Venant's theory and find out the displacement field and thereby the stress and strain in a non-circular cross-section shaft, we need to find a warping function psi which is going to satisfy criteria 1 and 2. Only then the psi, the solution for psi, will give you a true equilibrium solution which will satisfy the boundary condition. So, in nutshell we have to say that we need to find a psi which will satisfy these conditions, which will satisfy these two conditions. Now, if you look into these two conditions, it is very easy to satisfy the first condition. We can very easily find a psi which is a function of x and y and which will satisfy the first criteria. But it is extremely difficult to find a psi which will satisfy the second criteria. It is not, I should say that it is not impossible to find a psi which will satisfy the second criteria, but it is extremely difficult to find a psi which will satisfy the second criteria. Therefore, Sven-Venant's theory, the approach that Sven-Venant has given to solve the torsion problem of a non-circular shaft, though perfectly correct theoretically, it is often difficult to evaluate it or use it from the mathematical perspective, from the difficulty associated with the mathematics involved. So, in order to circumvent this limitation, a new methodology based on Prandtl stress function has been formulated or has been presented, which follows the same theory, which follows the same displacement field, but uses a new stress function which makes the calculation much more easier. So, let us move into finding out the what is Prandtl stress function and how it can be used to solve the problem of torsion of non-circular shaft. Before I move on to find out the Prandtl stress function and explain what it is, let me summarize the features of torsion of a non-circular shaft. The features of a torsion of non-circular cross-section shaft So, the shape of the cross section of the shaft is not distorted. Similar to circular cross section shaft, here also the in plane shape of the cross section is not distorted. But unlike circular cross section shaft, there is an out of plane deformation which is governed by psi xy. So, these are the basic features of torsion of non-circular cross section shaft. The essential difference with the circular shaft, as I mentioned earlier, is the out of plane warping. Now, let us look into the second topic, which is the Prandtl stress function. So, all of you all might be aware of the concept of stress function. We have all studied the Airy stress function in the context of elasticity. So, similarly, Prandtl stress function is the same form of stress function which is used to solve torsion of non-circular shaft. So, we will represent the Prandtl stress function by this symbol, which is the var-phi symbol. So, we can say that, let us assume that the shear stress tau x z the shear stress for non-circular cross-section shaft, let me write this as del phi by del y, where phi is this Prandtl stress function, as I have said before. So, now similarly tau yz, let me define it as minus del phi by del x, del phi by del x. So, these are the assumptions that we are making. Now, we know from the Sand-Venance theory that tau x z can also be written as g theta into del psi by del x minus y, and tau yz can be written as g theta del psi by del y plus x. This is already known to us. Now, let us see that this assumption or this consideration, do they satisfy the equilibrium condition. So, do the stress function written in this form, the Prandtl stress function written in this form, do they satisfy the equilibrium condition? This we have already seen that they satisfy the equilibrium condition. So, let me write down the equilibrium equation. So, the first one is now let us see what happens to this. So, sigma x is equal to 0, tau xy is equal to 0, tau xz is not a function of z. So, this goes to 0. So, therefore, this is satisfied. This is satisfied. Now, let us move to the second one. Here also we know that tau xy is 0, sigma y is 0, and tau yz is not a function of z. So, this derivative goes to 0. So, this equation is satisfied. So, let us see here that in this equation what do I have? Tau xz is in place of sigma z is equal to 0. So, this part goes to 0. Now, tau xz is del phi by del y, and this is minus del phi x by minus del phi by del x. So, this is my plus del 2 phi by del x del y, and this is minus del 2 phi by del x del y, and which is equal to 0. So, therefore, this equation is also satisfied. So, we can say that the expression for the Prandtl stress function or the assumption for the Prandtl stress function is satisfy all the equilibrium condition. Now, let us find out a constraint on the Prandtl stress function. So, we can say that del 2 phi by del y square can be written as g theta del 2 psi by del x del y minus 1, and then del 2 phi by del x square can be written as minus g theta del 2 psi Now, if I add this two up, then I can say that del 2 phi by del x square plus del 2 phi by del y square can actually be written as minus 2 g theta. Therefore, this is a criteria on the Prandtl stress function phi. The Prandtl stress function should be such that this equation should be satisfied. So, therefore, we can say that Prandtl stress function satisfies the equilibrium condition, and they need to satisfy this constraint given by equation 1. Let us see whether the Prandtl stress function satisfies the boundary condition on the lateral surfaces. So, let us check the boundary conditions on the lateral surfaces. So, as we know, similar to the torsion of circular shaft, for the non-circular cross section shaft also the boundary conditions, the lateral surfaces are force free. So, on the boundary x hat, y hat and z hat is equal to 0, which are the surface forces per unit area. Now, we know that x hat is equal to sigma x L plus tau x y m plus tau y z n. So, let me just draw a non-circular cross section. Let me draw the normal at any point n. So, this is the x axis, this is the y axis, this is alpha that the normal makes. L is cos alpha, m is sin alpha and n is equal to 0. Now, let us see whether this condition is sigma x is equal to 0, tau x y is equal to 0, now n is equal to 0. So, this is satisfied. Now, let us move on to the next boundary condition. Now, the third boundary condition has the problem. So, sigma z n is anyhow equal to 0, because both sigma z and n are equal to 0. Now, let us look into this. What is tau x z? Tau x z is del phi by del y, L is dy by ds. Similarly, sigma y z is minus del phi by del x, and m is going to be minus dx by ds, and that has to be equal to 0 for the boundary condition to be satisfied, which implies that this is d phi by ds is equal to 0. So, this boundary condition will boil down to d phi. This by the differentiation rule will end up being d phi by ds. So, if we use Prandtl stress function, the stress function just needs to satisfy that the derivative of the stress function on the lateral boundary, that is over here, needs to be 0. So, that can be easily satisfied if we can choose a stress function which is 0 on the lateral boundary. Therefore, we have now two constraints on the Prandtl stress function. The first constraint is del 2 phi by del x square plus del 2 phi by del y square needs to be minus 2 g theta, and d phi by ds needs to be 0 on the lateral boundary. Or this can either also be satisfied when phi is equal to 0 on the boundary. So, therefore, we need to find out a stress function which is going to satisfy these two criteria. So, if I can get hold of a function phi which varies in x and y, which is going to satisfy equation 3 and 4, then we have found out a suitable stress function which can be used to solve the problem of torsion of non-circular shaft. So, we can summarize this by saying that we need to find a stress function which is Prandtl stress function which satisfies this criteria. Now, you can observe that as compared to Sven-Venant's theory, where we need to find out a warping function psi which had a much difficult constraint to satisfy, or a much more difficult equation to satisfy, as compared to that, the Prandtl stress function has a much more easier constraint to satisfy, or much more easier set of equation to satisfy. Therefore, though the Sven-Venant's theory Sven-Venant's warping function and the Prandtl stress function both will give the correct solution of torsion of a circular shaft of a shaft with non-circular non-circular cross section, a Prandtl stress function is a much more easier approach mathematically. Therefore, most of the problem of torsion of non-circular shaft is solved using Prandtl stress function. Let us next find out whether this Prandtl stress function satisfies the boundary condition on the top and bottom surfaces. So, on the top and bottom surfaces of the shaft, L which is cos nx, M which is cos ny, and N which is cos nz. Now, N on the top and bottom surface is along the z direction. So, this is always equal to 0, this is always equal to 0, and this is equal to 1. Now, if you look into those boundary conditions on x hat, y hat and z hat. Let us look into this. So, I have sigma x L plus tau x y m plus tau x z n. Now, out of this, this goes to 0, this goes to 0, and this is left as tau x z. Similarly, this is which ends up, all the terms ends up being 0, this ends up being 0, sorry, this ends up being 1, this is 1, so it ends up being tau y z. Now, in the third equation, all the terms are equals to 0. Now, similar to a circular cross section shaft, we see that the top and bottom surfaces satisfies the boundary condition, except that x hat needs to be of the form of tau x z and the y hat needs to be in form of tau y z. In case of shaft with circular cross section, this was very easy to implement from practical point of view, because they would cancel out the opposite point. So, the force has to be distributed in this form, and the net force would be 0, giving rise to only a torsional moment. But it is not that straightforward for a non-circular cross section shaft, where there is not this form of symmetry which exists for a circular cross section of shaft. So, it is not obvious that x hat and y hat, the resultant x hat and y hat, because of the distribution similar to the shear stresses, will be equal to 0. In the next lecture, we will prove that though the cross section can be as arbitrary as possible, the resultant of this x hat and y hat will be equal to 0. So, we will do that in the next lecture, which will be lecture 7. Thank you.